What is the type of material generally? Is it brittle
Generally, it's a
material?
soft material, sir.
Yes, soft. Generally, soft or ductile. So whenever you have more work hardening tendency for the material, and the material is ductile, and you are operating at low speed, high depth of cut, high feed, just like the case of discontinuous chip. But discontinuous chip is obtained in case of brittle. So if you are applying those conditions here for the ductile material, so due to high friction, this material will go to the plastic state quickly and some portion will be sticking onto the cutting tool. It will alter the effective geometry of the cutting tool. So and the cutting tool life will be reduced ultimately. And the last type is the serrated chip. So that is formed for the materials which have very low thermal conductivity, like titanium alloy, nickel-based alloy. So whenever the materials are heat resistant, they are not thermally conductive. If thermal conductivity is less, then this serrated chip will form. And the different surface finishes also you have seen. If you have continuous chip, you have good surface finish. If you have discontinuous chip, surface finish will be poor and there will be irregular forces or forces will fluctuate, etc. And after that, we have seen the chip breakers. So why do we need to use chip breakers? So if you have long chip, you cannot handle it. It will cause some problem to the worker and workpiece, etc. So you have to break it. And there are various types of chip breakers. Natural and forced are there. Natural means the chip is coming and it will hit the workpiece or the flank face of the cutting tool and it will break due to brittle fracture. Then if it is a forced, then you can have these step type chip breakers, parallel step with radius and positive step, negative step, etc. We have seen various conditions for them. Under what conditions you will use a particular type of chip breaker. So those are the things we have discussed. Now let us proceed to the next topic, that is mechanics of machining or mechanics of metal cutting. So far we have seen the mechanism. We have understood how the chip is forming and under what conditions a particular type of chip is produced. Now we will see the mechanics. Mechanics means obviously we are talking about forces. So what are the different forces that are acting on the workpiece during cutting or on the cutting tool during cutting, and what is the amount of force that is required to remove the material, a particular type of material, at required machining rate, so etc. So here we will deal with the forces and some velocities, stress, strain, etc. So we will talk about those aspects. All those things come under the mechanics of machining. Now let us start that. So mechanics of metal cutting. So all of you observe the first figure. So when you are trying to cut the material, so for simplicity purpose, you can imagine some shaping operation. So this is the tip of the cutting tool, and this is the workpiece. TO is uncut chip thickness. uncut chip thickness. Okay, your intention is to cut the material up to the depth in one pass. And of course, V is cutting velocity. So gamma here is showing the rake angle. Okay. So alpha is showing the clearance angle. Now when you want to cut this workpiece, so tool is coming in this direction. So if you see carefully step by step, you go to the second figure. So whenever this tool is forcing against this workpiece, the material is getting swallowed. Not swallowed, swelling. Okay, the material is swelling. Then due to that bulging effect, material will go to plastic state. And if you observe, there is a plane AB now. Along this plane, the material will try to move. So if you observe the third step, now some portion of the material has moved along this plane. Okay, up to some small distance only. Now, within that time, tool will further advance and it will move little bit, and this will come up in this direction. So slice by slice, the material is moving in this direction. Okay. So ultimately, you will get this kind of chip. So this chip is anyhow showing the serrated type of chip. If you observe any chip very closely in the microscope, it will look like this only. Okay. At a macroscopic level, there will be some continuous chip like that. Otherwise, it will look like a serrated chip only. To understand this process better, one analogy was proposed by Paispanen. Here, the workpiece material is assumed to be like a pack of cards, okay, put together in this fashion. So, and these cards are making some angle phi with the horizontal plane. And now you are trying to move, okay, edge of the cutting tool in this direction. And what will happen? These cards will just travel in this direction, and at the same time they are moving in this direction also. Understand? They are just lifted up and they are going along this edge of the cutting tool or the rake surface of the cutting tool. Rake surface, okay, of the cutting tool. Now whatever angle that is there, okay, the slippage is taking along this plane. So now angle between the horizontal plane or the cutting velocity, you can say, this is the direction of cutting velocity. Angle between this cutting velocity and this plane is called shear plane. So shear plane on the horizontal surface or the cutting velocity. So that angle is called as shear angle. Phi is equal to shear angle. Okay, don't get confused with this phi and the side cutting edge angle phi. Okay, so both are different. So this is how you can understand the chip formation mechanism. Okay, so this is one kind of analogy given by Paispanen. Now for simplicity purpose, okay, for easy calculations, we are assuming that the cutting process is orthogonal process. In reality, obviously, many cutting processes will be oblique in nature, but the difference, okay, between the forces that are acting in orthogonal cutting and oblique cutting, difference is less, okay, not very high. So if you want to get some approximate value, okay, it will be close to the exact value. So you can choose the orthogonal cutting process. So now we will try to analyze the orthogonal cutting process. So there are many assumptions in orthogonal cutting process. You can see we assume that the tool is perfectly sharp and there is no contact along the clearance face. So the tool, okay, this is the cutting edge if you're talking. So this cutting edge is perfectly sharp and there is no contact at this area. Okay, in this area, flank surface is not at all in contact with the workpiece. Next is shear surface is a plane extending upward from the cutting edge. So shear plane, if you see, this is the shear plane. So this is in the upward direction and it is originating from the cutting edge. Because you can see, of course, in reality, there will not be any fine single plane, shear plane. In reality, there will be some volume of the material which will be moving, not a single plane. But for simplicity purpose, again, it is assumed as a plane because it will be very thin. Now, the cutting edge is a straight line extending perpendicular to the direction of motion. So, cutting edge is perpendicular to the cutting velocity. Chip does not flow to either side. So, chip will flow along this rake face only. It will not move in this direction or in this direction. So, that means plane strain condition. Straining of the workpiece material is taking place in 2 dimensions only. It is not moving in the other direction. So depth of cut is constant. You are not varying the depth of cut. That is, in this case, it is TO. The width of tool is greater than that of the workpiece. That is also one feature of orthogonal cutting. So then only the chip will move along the rake face. The work moves relative to the tool with uniform velocity. So there is no change in the velocity also. We assume that workpiece is moving with the uniform velocity. A continuous chip is produced with no built-up edge. So this is also one assumption. Therefore, continuous chip with no built-up edge. The shear and normal stresses along shear plane and a tool are uniform. So if you consider the shear plane, so shear stress and normal stress. You can see here you have one shear plane. So in this plane, whatever stress is there, that is uniform throughout. And normal stress is also uniform. So those are the assumptions. Now let us try to analyze this orthogonal cutting process. So as I told you, TO is uncut chip thickness. LS is length of shear plane. From this point to this point. TC is cut chip thickness or simply chip thickness. TO is uncut chip thickness. LS is length of shear plane. Gamma is anyhow rectangle in this case. So tool, chip and workpiece are like this. And phi is shear angle. Now we are drawing this A, B, and we'll take a vertical here and we'll see the triangle. Okay, if we A, B, so A and B are like that. If you draw a vertical line, that is nothing but the height TO. So we have joined B. This is representing phi. And here if you see from the vertical, okay, if you take this gamma angle, that can be shown in the diagram like that. And now what is TC? So TC is the thickness of the chip, which is perpendicular to this face. Understand? TC is not equal to this AB, not equal to that. So after turning, so if you take from this point, if you take a vertical onto this surface, so whatever you are getting here, that is the thickness of the chip. Okay. LS is different, TC is different. Now let us try to define this chip thickness ratio. Chip thickness ratio is nothing but the ratio between TO and TC. Okay, uncut chip thickness divided by chip thickness. Now let us see the relation. Now if you see this carefully, now what is this angle from here to here? Okay, before that, okay, now, yeah, I think all of you can say this angle. Okay, what is this angle? What is the amount? In terms of phi, gamma, what will be this angle? Anybody? Very simple.
90 minus 5, sir.
Yes. So this is 90 minus 5. So this is gamma here. This is 90. Now what will be this angle? What will be that? If you say that as x, suppose. So that is total angle should be 180. So 90 minus 5, that is plus gamma, that is minus 5 minus gamma. Okay. So that is the angle. Now our intention is to get the ratio between TO and TC. Now how do you get that? So same angles, whatever I have written are shown there. Okay. So here total angle is 90 minus 5 minus gamma. Or it will be plus gamma if you take it inside the bracket. That is okay. Now we will use these two triangles and try to get the relation. What is the common thing in these triangles? That is AB. Its length is LS. Okay. In different ways you can get it. So I'll say you can consider For our convenience, we can give some name here. So if I take sine phi, it is TO by LS. Similarly, if I take again sine phi minus gamma, instead I will take cos phi minus gamma, that is TC by LS. So from here, LS is equal to T0 by, or otherwise, I'll take T0 equal to LS sine phi. So from here, TC is equal to LS cos phi minus gamma. So simply take T0 by TC. So these two will get cancelled. So it will be sine phi by cos phi minus gamma. This is represented with small r. So that is called chip thickness ratio. Okay. Now chip thickness ratio is less than 1. Okay, it will be always less than 1 because cut chip thickness TC is always greater than T0. Okay, why? Because some bulging of the material is taking place and the length will decrease and its width will increase because of friction. Also, it is trying to push this material downward and it is increasing the width of this area. So that's why TC is always greater than T0. Okay. Now, if chip thickness ratio is high, what can you understand? If chip thickness ratio is high, it is not beyond 1, but if it is high, what is the meaning? What can you understand if chip thickness ratio is high? What can you say? If chip thickness ratio is high means T0 is very high compared to TC. Okay. Compared to TC, T0 is high. Sorry. T0 by TC. Okay, TC is high. Okay. Sorry. So if your chip thickness ratio is high, so that means T0 okay, is on the higher side and TC is less. But TC is less means that doesn't mean that TC is less than T0. Okay, its absolute value is less. So there is not much difference. Okay. And let us say if R is less, okay, chip thickness ratio is less. So then you can say, in the first case, they are close to each other. T0 and TC are very close to each other. So if the chip thickness ratio is less, in other words, So when will this TC be very high? So that is better way of putting the things. When will this thickness will increase? TC is always greater than TO. This is fixed. Okay. But when will you have large TC? When will you have high amount of TC for the same material?
The depth of cut is high, sir.
Depth of cut is high. Okay, that is correct. And in other words, if the depth of cut is high, what are you doing? You are spending more energy during cutting process. Understand? Let us say depth of cut is constant. For the same depth of cut also, you can have different TCs. Okay.
Sir, at low speed, sir.
Yeah, we are operating at low speed and high power consumption is there. There is a great friction between the chip and the cutting tool. Okay. So this is the meaning. If the TC is very high. So if TC is very high, what is happening to R? R is a small value. Okay. So if you have very small R of chip thickness ratio, you can understand that, we are spending more energy during cutting process. So that is the significance of chip thickness ratio. Okay. And if R is high, you are spending, that means T0 and TC are very close to each other. So that means you are spending less energy during cutting process. There is less friction between the chip and the tool. Okay, that is the meaning. So that is why we are measuring the chip thickness ratio, and with that you can understand the mechanism involved. Is it clear?
Yes, sir.
Yes, sir.
Okay. So same thing, whatever I have shown, chip thickness ratio R is T0 by sin phi. That is also equal to TC by cos. So ultimately this is the formula you have to remember. Okay, based on this we'll solve some problems later on. Now we have seen that chip thickness ratio R is equal to sin phi by cos phi minus gamma. So that is also equal to Vc by V. Now what is Vc? Vc is chip velocity. V is cutting velocity. Now how this R is equal to Vc by V? Okay, this we will see in the next coming slides. In the coming slide, I think we will see why this Vc by V is becoming sin phi by cos phi minus gamma. So for the time being, you understand that Vc is chip velocity, V is cutting velocity. So now you have to understand that chip velocity is different, cutting velocity is different. Okay. So chip velocity is less than the cutting velocity. Chip velocity is always less than the cutting velocity. Why? Any reason? So main reason is because when the chip is trying to flow away, or going away from the cutting zone, this tool is trying to pull this workpiece in the downward direction due to the friction. Okay, so there is a friction between the one side of the chip and the rake surface. So that is slowing down the movement of the chip. That's why chip cannot flow at the cutting velocity rate. So Vc is always less than V. So this we'll see later. So now if you arrange this, okay, rearrange this, you can find 5. Okay, sometimes you need to find the shear angle 5. Now, none of you can do this on your own. So I am rewriting this equation again. R is equal to sine phi. Now expand this cos phi minus gamma. What will it be? Cos phi cos gamma plus sine phi sine gamma. Okay. So if you take this, you can write sine phi is equal to R cos phi cos gamma. Just for your understanding, I am doing all this. Otherwise, directly you can write this. So R sine phi sine gamma. Okay. Now, if you divide by cos phi on either side, so this will become tan phi R cos gamma plus R tan phi sine gamma. Okay, I have divided this equation with cos phi on either side. So you can write now R cos gamma is equal to 1 minus R sine gamma times tan phi. Okay, I have taken this on this side. So now from this, you can get tan phi is equal to R cos gamma by 1 minus R sine gamma. So you have to, okay, remember this relation also. So if you want to find shear angle phi, so it will be tan phi is equal to R cos gamma by 1 minus R sine gamma. Okay. Now, how do we find R? That is chip thickness ratio. If you want to find, it is sine phi. This equation we have to use. But is it possible to use this equation? But shear angle, okay, look at, you need to get this shear angle to find out R. Now, how will you get this shear angle directly? Our intention is to find the R. So it is very difficult to get the shear angle. Okay. Experimentally, after doing the experiment, we cannot measure the shear angle just like that. So it is difficult. So if you want to experimentally find the chip thickness ratio, now let us see the procedure. Okay. So here, volume of the material, okay, let us say you have taken one slab or one workpiece and you have removed this amount of material from this. Okay. Now you know the volume of this material that is removed from the workpiece. So its thickness is T0. You know its width, that is WO, and you know its length, that is LO. Okay. So you know the volume of the material before it is removed, and it is equal to the volume of the material that is removed. Okay. So what is the volume of the material that is removed? TC is the thickness of the chip. WC is the width of the chip, LC is the length of the chip. Okay, length is reducing and thickness is increasing in the ideal orthogonal process. And WO and WC are almost same. There is no change in the width. Okay, if there is a change, there is the movement of the chip in lateral direction. So now the process cannot be orthogonal. So we assume that WO and WC are equal. So from this, now you can say TO by TC. Okay, these are almost equal. TO by TC is equal to LC by LO. Now if you divide this LC by LO with the time, like LC by unit time, LO by unit time. Now what are these? VC by V. So R is equal to VC by V also. And LC by LO is more important for us. Now what is this T amount of time required for removing this slab? It is indirectly nothing but giving the velocity, cutting velocity. Okay. Now you can find the length LC because once the chip is removed, you can find its length even though it is in some this kind of form. You can measure the length of it using some microscope. Okay, you can project this on some surface and you can measure the length of a curve. Understand? Or using some thread you can measure the length of this chip. An uncut chip thickness, chip length, anyhow you can measure. This is the length of the slab. So experimentally it is easy to measure LC and LO. So you measure those and take the ratio. So that will give you R. That is also equal to VC by V. Now once you find the R, you can easily find phi now. Okay. So because tan phi is equal to that equation we have seen. Okay. R cos gamma by 1 minus R sin gamma. Now the next one is, so once you know R, once you know phi, so you can find now shear strain during chip formation. So material is getting strained, then only the chip is getting formed. Now let us see this. So you take one slice of the material, so that is being removed. So this one, consider this. So here you have the rake surface. So this is the tool. Okay. This is the uncut portion. This is the workpiece. Okay. So this is a TO. Okay. Now you consider this triangle ABC. Okay, let us just see step by step. Consider ABC. For better clarity, I will remove all the ink. So if you see here, so what is this angle? Equal to this angle, that is gamma, or the rake angle. So here it is gamma. So same gamma is shown. Okay. So this is anyhow, here this is phi. And this is also phi. It is a horizontal, AB is horizontal. So that is phi. Now, if you take one perpendicular onto this AC from B, that is meeting AC at D. Now this is gamma. Okay, this is 90 degree and this is phi. So if this is phi, of course this is also 90. This is definitely 90 minus phi. Okay. So here this total angle should be 90. So you can and if you assume this as x, okay, so x is equal to 90 minus 5 minus gamma. So this is nothing but 5 minus gamma. So this angle is 5 minus gamma. Okay. Now if you want to find the shear strain, for that only you are doing all this. Now what is shear strain according to the definition? So it is the displacement, that is AC. So initially material is like this. Okay. So but it has displaced to a length of AC. So that is the displacement by the distance between the two ends of that plane on which the shear force is acting. Okay, that is BD. So AC by BD is shear strain, that is represented by this zeta symbol. Now what is AC? AC is AD plus DC and BD remains same. Now what is AD by BD? AD by BD. AD by BD. You consider this triangle. So that is nothing but cot phi. So AD by BD is cot phi. And similarly DC by BD. DC by BD is tan phi minus gamma. And DC is the opposite side for this phi minus gamma. So tan phi minus gamma. Now this is how we will estimate the shear strain zeta. Okay, once you know phi and gamma. Gamma is anyhow known to us because that is tool dependent rake angle. Now the next is velocity relations. So we know that this is the cutting velocity direction. This is the Vs. That means, okay, chip velocity along the shear plane. Chip is not only moving, okay, in this direction only, it is also moving in this direction, okay, at very slow velocity. So this is Vs. So chip velocity is along the rake face, that is Vc. So now you consider this velocity triangle. So that is V. It is Vs. That is Vc. Okay. Instead of considering it here, you consider this location. Vc. And that angle is gamma. Now find out the remaining angle. So that is 90 minus gamma because total is 90. So what will be the remaining? 90 minus 5 minus gamma because total angle is 180 degree. Now you can apply sine rule. So what is sine rule? Sine phi is equal to, okay, otherwise, of course, you can apply in different ways. So you will say Vc by sine phi. Vc and opposite to that is phi. So Vc by sine phi or sine phi by Vc, both are same. So if you consider that way, that is okay, that is also fine. So I'll say Vc by sine phi is equal to V by sine 90 minus phi minus gamma. So that is nothing but cos phi minus gamma. Similarly, Vs by sine 90 minus gamma, that is cos gamma. So this rule you can apply here. And from this also you can get the relation. What is our Vc by V? So now here if you consider Vc by V, so this is sine phi Vc by V. So you consider these two. You are taking this V, so this is nothing but sine phi by cos phi minus gamma. So that's why R is equal to Vc by V. That is equal to sine phi by cos phi minus gamma. If you want the Vs relation also, you can find. So I think better we stop here. So next is merchant analysis, where we will see different forces acting on the cutting tool, and we will try to find the relation between those cutting forces, and ultimately we will find the power requirement for the cutting process. So those things we will see in the next class. So whatever is shown here, all the mechanism and mechanics, they are very, very important in terms of your academics also. That means if you are writing any exam related, competitive exam, so definitely, so few questions may be asked, and in your interviews also. So if you are talking about a metal cutting or any manufacturing process, you may be asked regarding the tool signature, what is the significance of merchant circle, what is the relation, what is this R, etc. All these things are very, very important in the academic point of view, and when you are facing some interview also, public sector interview or private these private companies also, they will ask these questions. So one of your seniors also have informed me last time. So many questions were asked from this subject during his interview. He is a Rutvik, 2020 pass out. Okay. So this subject is very important. So all of you pay attention. If you have any doubts in this, you can ask. So I hope all of you are following the classes. So if you have any difficulty, please bring it to my notice. Okay. So I'll try to change the teaching method or something. Okay. If it is not teaching to you. Otherwise, I assume that you are getting what I'm teaching, and everything is fine. Okay, that's all for today. Thank you. Have a good day.
Thank you, sir.
Thank you, sir.